Hi everybody. This, this lecture we, in this lecture we are going to talk about Joblanski diagram. So it's a very important topic as far as photochemistry is concerned. So it mainly talks about the absorptions of electromagnetic radiations. Absorptions of electromagnetic radiations. So as per our definition, it is an energy level diagram arranged with the energy on vertical axis. Vertical axis. It shows a portion of consequences of applying photons from visible light to molecule under consideration. See, when you pass the light radiations to a molecule, the molecule absorbs the light radiations and goes to excited state. So, what is excited state? Excited state is a energy level with high energy. Yeah, high energy. Therefore, another question arises. So, what is meant by ground state? When the molecule is in, what is meant by ground state now? The molecule is in the stable state. Okay, so that is called ground state. So next thing. So what are the various processes associated with the Joblanski diagram? So one is internal conversion, and another one is fluorescence. Next thing is intersystem crashing, and another thing is phosphorescence. So before going into Joblanski diagram, so we have to learn something about spin multiplicity. Spin multiplicity. So actually, spin multiplicity is only a quantity. So it is represented by the formula 2s plus 1, where S stands for total electron spin. Total electron spin. So based on the spin multiplicity, we can classify the qualification of electron as singlet ground state, and singlet triplet state. See, the most of the molecules have even number of electrons in the ground state. So according to the Hund's rule and the basic idea of electrons, most of the electrons are paired, that is the spin paired in the ground state. When the spins are paired, the upward orientation of the electron gets cancelled by the downward orientation of the electron spin. Okay. So one more thing I want to say here. So when the electron is represented by the upward orientation, it is given the value, it is given the spin quantum number value of plus half. At the same time, the downward orientation of the electron spin is represented by the value minus 1 by 2. So that is S1 stands for upward orientation of electron spin, whereas S2 stands for the downward orientation of electron spin. That is S1 stands for plus half and S2 stands for minus 1 by 2. So when you are going to calculate the spin multiplicity, that is the total electron spin, yes, the formula is S1 plus S2, that is plus half and minus half. So S1 value is plus half and S2 value is minus half. So therefore, total electron spin value is 0. Therefore, next our job is to calculate the spin multiplicity. So that is 2s plus 1. So you substitute the value of s, that is 0. Therefore, 2s plus 1 is equal to 1. So when the spin multiplicity of the value is 1, the molecule is in singlet ground state. The molecule is in the singlet ground state. So next, let us calculate the triplet excited state. Triplet excited state. If the spins are parallel, say if the S1 value is plus half and the S2 value is also plus half, therefore the total spin is calculated as S1 plus S2, that is plus 1 by 2, and another plus 1 by 2 gives 1. Therefore the 2s plus 1 value becomes 3. When the spin multiplicity of the molecule is 3, then it is called triplet excited state. Triplet excited state. So I told you already, excited state means the molecule is in the higher energy state. See, when a molecule absorbs the light of suitable energy of h nu, one of the paired electron goes to excited state. The spin orientation of the two electrons may be either parallel or anti-parallel. When the spin orientation of the two electrons is parallel, it is in the triplet excited state. When the spin orientation of the two electrons is anti-parallel, then it is in singlet ground state. Singlet ground state. So this is the schematic representation of the Joblanski diagram. So when you see the Joblanski diagram, you could find the values S0, S1, S2, S3, T1, T2, and T3, where S0 stands for singlet ground state, S1 stands for singlet excited state, S2 singlet excited state, but in the second energy level, S3 again singlet excited state, but in the third energy level. So next one, T stands for triplet excited state. T1 triplet excited state with the energy level 1. T2 triplet excited state with the energy level 2. T3 stands for triplet excited state in energy level 3. So other things you could witness, internal conversions, intersystem crashing, fluorescence, and phosphorescence. So first, an electron can jump from, on passing the electromagnetic radiation, an electron can jump from ground state to higher energy level. So depending upon the energy of the photon absorbed, we get a series of singlet excited state and a triplet excited state. So one more point you have to remember. So it is not necessary for all the molecules or electrons to, it is not necessary for all the molecules to absorb all the passed light energy from the source. So the electron can absorb a portion of the light radiations from the source and go to the excited state. Generally, the singlet excited state has higher energy than the corresponding triplet excited state. So it is shown here as follows. That is, the energy of the singlet excited state is greater than the energy of triplet excited state. Similarly, ES2 has higher energy than ET2. Again, energy of the S3 is greater than energy of T3. So it is represented here. So for example, the energy of the S3, the energy level of the S3 is here. Energy of S3 is here. Wait a minute. So this is S3. The energy level stands here. Similarly, you just consider T3. The energy level of T3, that is the energy level of T3 is here. So the energy level of S3 is greater than energy level of T3. Similarly, energy level of S2 is greater than energy level of T2. Similarly, the energy level of S1 is greater than energy level of T1. So all these things are collectively represented by a single diagram called Joblanski diagram. So what are the things happening in internal conversion? What are the things happening in intersystem crashing? Things happening in fluorescence? What are the photochemical changes that take place during phosphorescence? And everything is collectively represented by Joblanski diagram. So that is the specialty of this topic. So next, what are the types of transitions? For example, when a molecule absorbs light radiations, the electrons may jump from singlet ground state to S1 or to S2 or to S3. Okay, the transition may take place from S0 to S1, S0 to S2, or S0 to S3. So this depends upon the energy of light radiations. Okay. So for each singlet state, there is a corresponding triplet state. So this is mentioned by me in the previous slide itself. For S1, you have T1. Similarly, for S2, T2 is there. Similarly, for S3, you have the another excited state, namely T3. The molecule is in singlet or triplet excited state is said to be activated. Okay, so when the molecule is in S0, it is in ground state. When the molecule is in singlet or triplet excited state, it is called activated state. So it is collectively represented by A asterisk. Okay, so next, so now the molecule is in the activated state. The activated molecule returns to the ground state by emitting its energy through the following type of transitions. There are two types of transition. One is non-radiative transition and another one is radiative transition. Radiative transition. So first, let me talk about the non-radiative transitions. So in non-radiative transitions, there are two types. One is internal conversions and another one is intersystem crossing. So in internal conversions, this type of transition involve the return of the activated molecule from higher excited state to first excited state. Okay, they are represented as follows. For example, when the molecule or electron is in S3, it returns to S2 or S2 to S1. That's all. S3 to S1 or S2 to S1. Similarly, T3 to T1 or T2 to T1. Okay. So next thing, the energy of the activator molecule is given out in the form of heat through molecular collisions. Through molecular collisions, the energy is released. Next, this process is called internal conversion. Internal conversion occurs in less than 10 to the power of minus 11 seconds. Minus 11 seconds. Okay. So next one is intersystem crossing. Similarly, the molecule can also loses its energy by intersystem crossing. Intersystem crossing involves the return of the activator molecule from the state of different spin multiplicity. Okay, S2 to T2 or S1 to T2. Actually, this is a forbidden transition. This is a forbidden transition, but it occurs relatively at slow rate. It occurs at slow rate, but the intensity of this transition is not clear. Okay, it is not up to the standard. Since these transitions are forbidden, it occurs in a slow manner. Slow manner. So next one is radiative transitions. So in radiative transition, we have two types. One is fluorescence and another one is phosphorescence. These transitions involve return of the activated molecule from singlet excited state S1 and a triplet excited state to ground state S0. This accompanied by emission of radiations. Since the radiative emission occurs, these transitions are collectively called as radiative transition. So now let us consider fluorescence. Fluorescence emission originates due to the transition from singlet excited state to ground state. Singlet excited state to ground state. For example, S1 to S0. S1 to S0. So what is the next characteristic feature? It is an allowed transition. It is an allowed transition. This transition is very fast. It occurs in 10 to the power of minus 8 second. 10 to the power of minus 8 second. So one more thing, the fluorescence stops as soon as the incident radiations are cut off. Okay, so this phenomenon stops as soon as the incident radiation is cut off. So what are the examples? Fluorite crystal, fluorite. Eosin is a dye. Okay, eosin dye shows fluorescence. And another thing, fluorescein, it's a green colored thing. So it also shows fluorescence. Fluorescent dye also shows the process, namely fluorescence. Next one is phosphorescence. Phosphorescence arises due to the transitions from triplet excited state to ground state. That is T1 to S0. It is a forbidden transition. Forbidden transition. I told you already. Allowed transition takes place in a fast manner. Since phosphorescence is a forbidden transition, it occurs in slow manner. Phosphorescence continues for some time, even after the incident radiations are cut off. Okay. So even if you switch off the electromagnetic radiation, this process continues for some time. Example, zinc sulfide crystal and alkaline earth sulfides. Alkaline earth sulfides. You know what are called alkaline earth metals? Huh? Calcium, magnesium, so like that. So the alkaline earth sulfides show a very good property of phosphorescence. Okay, so these are all the some of the references that you could gather information about Joblanski diagram. One is a well-known book, namely Puri and Sharma, and another thing is Sony and Dharmara. Dharmara. Okay. Thank you, students. Thank you. So let me meet you with some other videos. Thank you.